To understand how we are returning to the moon, we first have to look at the baseline established by the Apollo missions. Those missions were designed for brief, temporary visits. The spacecraft and the control sensors guiding them relied heavily on manual, analog systems. Once on the surface, the astronauts faced severe power constraints. Electricity was generated using fuel cells that combined finite, preloaded supplies of hydrogen and oxygen. When those supplies ran out, the mission ended. We ultimately left the lunar surface because we lacked the technology and the renewable infrastructure required to stay. The objective today is different. The goal is to turn the moon from a brief destination into a sustainable workplace. Pushing the necessary infrastructure into deep space requires a massive heavy lift vehicle. The Space Launch System rocket serves as the transportation backbone for this new architecture. Sitting atop that rocket is the Orion spacecraft, which operates on a fully digital architecture. To navigate autonomously, Orion relies on 4 redundant, radiation-hardened flight computers. Orion also solves the historical power problem by using renewable solar cells to capture energy directly from the sun, freeing the spacecraft from the strict resource limits of the 1960s. In 2026, the Artemis II mission will take a crew on an orbital flight test to validate this deep space highway. By utilizing renewable energy and autonomous navigation, the Space Launch System and Orion form a complete platform designed for long-duration deep space travel. Getting to lunar orbit is only the first step. Moving a crew safely down into the gravity well and back requires a reliable landing vehicle. To mitigate the risk of that descent, NASA will demonstrate the human landing system in low Earth orbit before committing to a lunar landing. This leads to Artemis III in 2027, utilizing commercial partners like SpaceX and their Starship platform for a critical demonstration in Earth orbit. By proving these massive landers operate correctly near Earth first, engineers ensure maximum system maturity before human lives rely on them in the lunar environment. Following those tests, Artemis IV, planned for 2028, will mark the return of astronauts to the lunar surface. They will bypass the equatorial plains and head for a specific target, the lunar South Pole. This region contains deep craters with permanently shadowed regions. Inside these dark basins, temperatures drop low enough to trap frozen water and other volatile compounds. These subsurface ice deposits provide the raw materials needed to sustain a long-term human presence. Extracting them will be difficult. The South Pole is a hostile environment, characterized by extreme temperature swings and low-angle, harsh lighting conditions. The exposed, unpressurized rovers used during the 1970s would not survive here. Navigating this terrain requires advanced, environmentally protected lunar terrain vehicles and robotic surface assistance. Operating in this resource-rich laboratory demands completely new levels of mobility and thermal protection. Beyond the initial landings, the objective shifts from short-term survival to establishing a continuous operational base. This requires a staging backbone in orbit, anchored by the Gateway space station, alongside a dedicated communications grid known as LunaNet. This chart shows the critical vulnerability of any lunar surface operation, the lunar night. Once the sun sets, solar power generation drops to zero for 14 consecutive days. To survive this freeze, engineers designed a deployable 40-kilowatt fission surface power system, providing continuous output regardless of sunlight. For crew safety, a specialized rover chassis transports the active reactor a full kilometer away from the habitat before activation. Bridging that separation distance requires a custom, high-voltage transmission cable to deliver power without adding unlaunchable mass to the payload. That continuous fission power is the absolute linchpin. Without it, surviving the lunar night and establishing operational permanence is impossible. With a high-output power grid online, the base can begin in-situ resource utilization. This process allows the outpost to extract its own water, oxygen, and rocket fuel directly from the lunar regolith and ice deposits. By producing its own critical supplies, the base transforms into an autonomous, sustainable, self-fueling outpost on another world. Artemis is the vital construction phase. We are laying the concrete and testing the specific technologies required for humanity's eventual jump to